Afternoon. The original processing software was called Livia. It was DOS based, and you'd end up with text files. You can see here, this is where you did all the setup, sampling control of the program. It was clumsy. It was bulky. It was kind of hard to use. You do kind of all the same stuff that we've been talking about. You have to type in your laser wavelengths. You have to do your clock calibration in this format. Some of us know what DOS is. Some of us probably don't. And then it would put out a text file that looks similar to that. Yeah, I have almost no experience with this old program. My experience is 99% with the new program that you guys have now. Just kind of shows you some of the history of like where it came from and how much better G9 is. The advantage of the new program, or G is the name of the program, we're up to version 9 now. I'm not sure if we did 1 through 8 before that, but we definitely did a few iterations, 3, 4, 5, something like that. It is a Windows-based program, and that allows us to have all the latest and greatest drivers. You can do some pretty fancy graphics, as you've already seen. Display all the status stuff that you need in real time. Better control of reprocessing, the parameters and everything built in. All the earth tide and ocean loading functions are built in, and like I mentioned, it is accepted by the gravity community. It's what BIPM uses on their absolute gravity meter. There's gyrrometers, NOAA, NRC, etc. Replaying old Olivia data in the new G software is not available. You can do older versions of G software data. So if somebody had a copy of the set of data from like G5, you can pull that into G9 and reprocess it and rerun it. Can't go the other way. So if you have G9 data, you can't reprocess it on G5 software. We kind of talked a lot about this. Our project is composed of sets. Sets are composed of drops. Kind of typically we do 100 drops per set, and again 24 sets over 24 hours is kind of standard, and that helps to eliminate any errors with time. As we've seen already a little bit, there's several ways to start a new file. You can start from a raw project file, meaning nothing is saved over from the last run. You can make templates. We'll kind of go over that here in a little bit. I think with your specific, what you're going to be using the instrument for, that might be a great thing to do. So each one of your core sites will have a template. When you get to the site, you pull up the template. You can start running pretty quickly. It's got all your lat long saved. It's got your elevation saved. You already have your name of the site and that sort of thing. So yeah, I think templates will be very useful for you. The other thing you could do is use the existing project from the last time you were at the site, similar to the template. The nice thing about the template is it's just already set up previously back here at the lab. We'll go over starting project, monitoring data acquisition, storing the acquired data. Actually, that's just saying that you can do all that in that program. Yep.
And with regards to this template and the like, do you have any idea what Dan Winister does?
No, I don't. But I think Derek has taken all that over. So a quick email to Derek would definitely be able to answer that question. My guess is Dan just starts from the previous file, and then changes parameters based off of the previous file. But again, my expertise is in application, so I don't know if it would be better to send templates. I can see benefits for both, and really, it's only a matter of you got to put a little bit of legwork ahead of time in for the template that you normally would do in the first time you go to a site. So, sorry, I know that's that's a no answer, but yeah, kind of application. We're not out in the field with these very often, so we have less experience with kind of what works better than the other. So starting from scratch, you can see here. Actually, no,
It's like a laser pointer, but
the other one did. Green. That would be. So if you start from a new project, you can see you have to enter all the parameters in. So we kind of did that this yesterday morning. It had information for Microgene. Turns out it's about 40 minus 105. You'll need to, your polar coordinates are 0. You'll have to put all that in. Lat, long, elevation. You'll need to know your local gradient, and it all has to be manually typed in. We do have a conversion to go from degrees to decimal, and that is all converted internally. Oops, apologies.
Right.
Yes.
There was a blank 2 slides back
Okay.
for radial coordinates with polar coordinates. What's that relative to?
That's the North Pole.
Oh, that's the wobble?
The wobble of the Earth. Yep. Yeah.
Got it.
And they give a sorry.
So the ones that we've already done, we entered actual,
X1.
yeah, but we entered actual numbers there instead of just leaving it here.
Right, and well, this page is showing you that if you start from scratch, you're gonna have to type in a bunch of information. Polar coordinates need to be updated on a regular basis. So even if you as I go on, you'll see that in templates and stuff like that, you'll still need to type in. You'll have to change your polar coordinates. So,
What you can do is I've got the web address that you can get on Bell Parish as well as the U.S. Naval Observer.
yep, it's this guy right on here.
Once you get on their mailing list, just get it on your cell phone. You can get up off your cell phone and see what the offset is for today. They send it out once a week.
So on our
And it's a prediction for a month ahead of time.
on our website, I told you guys the other day on our website under support we have the polar
Yeah,
coordinates. as
that's
well.
how we got it yesterday.
Yeah, so this one will tell you, our website will only tell you the polar coordinates for that day. It updates and pulls them off the web every day. This one will actually tell you the coordinates for future days. So if you know you're going to occupy a site on the 15th, you can go on there and already have them, either write them in your notebook, or if you need templates like we'll get to in a little bit, you can actually type it into the template ahead of time. So, good questions. Anything else about those parameters? Yep, so we can do converts degrees, minutes, seconds to decimal degrees, as well as converts UTM coordinates to decimal degrees. This window pops up if you click the convert button right there. On the system tab, there are a couple of different selections you can select FG5, FGL, A10, and this is an older system that no longer exists. Most of this should be filled in. Again, if you start from scratch, you'll have to fill this in the first time. The WIO stuff, the wavelengths are always the same for the WIO. As you saw, each time you'll have to fill in the 1F values. The ML1 is a different laser that can be used on the FG5. It's not iodine stabilized. It's only the front half of the helium neon part. We do make those at Microgy as well. Some people will buy them as a backup later, but it takes your 2 microgal meter and makes it a 10 microgal meter. So at that point, the ML1 becomes the kind of the limiting factor. The A to D is now handled all through the USB. That was the cable that we forgot yesterday, and it wasn't communicating. So all these channels look a little bit different if you're using USB straight into the SIMX as opposed to an A to D card that was at one time handled in the Xbox. You can also set your fringes in. Oh, I thought it was a picture there. In this window, so on the System tab, if you click on Setup, you'll get a dialog that pops up, and you can change your prescale and the total number of fringes that get acquired. We suggest this kind of standard numbers here, and most likely those don't need to be changed. We wouldn't suggest changing those numbers at all. So
Question for you. When you were saying template, with respect to these settings and like, is this a text file that it can read from, or this is you set this up once and then you just copy from that?
So you, if you want to make a template, you would put in all these values and
Like
then
this.
sit like this.
From these individual pop-ups.
Yep. And then you would save as a template,
Gotcha.
and then that would save an FG5 file template.
Right.
And then-
There's not a separate configuration file to do that.
Right. The program creates the configuration file as well. Yeah. So these are all in there. We started from a project yesterday, an old project from Microgy. So these numbers are set. I would just use what's in the file. These could be a little bit different than what we have in your file. So stick with what we got there.
Stick with what you have where.
What we have on the computer,
Okay.
as of now. And actually, now might be a good time to flip back, and so I've got the data here on my computer. All right. So this is the data that we took last night, and you can see what was I going for here? Fringes. Go to Setup, System, Fringe card. We're doing a 100 prescaler and collecting a total of 2,700 fringes. The old numbers were back when computers were much slower and you can't take as many fringes, get as much data. So this is just much higher resolution data. Again, I would just stick with 100, 2,700, and you'll be all set there. Under advanced on the system page, it's hidden back behind here. There's a pop-up window that you can adjust your factory height. Those are the numbers that don't change. That was the B and D in the schematic the other day. That comes from when we build the system. 115 is for an FG5. I think the FG5X is 125. Is that what you got?
125, 183.
Yep. So that shouldn't change unless it comes back to Microgy and something changes in the setup and the height of the basically that top rod ring there will set that distance. Your clock frequency might change over time, but when Rubidium clocks are brand new, they're almost perfect 10 megahertz.
We've got exactly on the basic on the front of this thing. So is this does that feel integer or floating?
You have several decimal places.
You do?
Yeah, I don't know if you have. I don't think you have
Zero point
infinite.
zero
but-
zero two one on it.
It's in there already.
Yep. And so that's a difference of 0.1 microgal, if I do the math correctly. So that's if you put in a perfect 10 megahertz and your clock is actually 0.002. It's a difference of, yeah, I can't do the math quickly in my head, but it's about 0.1 microgal. So, but because you have that value put into the system, you're reading the right value. To calibrate that clock, we do that at MicroG. Anytime it comes back for service or repair or extended maintenance, we just monitor it compared to a GPS, either rubidium or cesium clock, and we can see what the difference is in between a good 10 megahertz, a perfect 10 megahertz clock, and this clock, and that slip time tells us our frequency. I'm sorry?
You are at Fort Collins.
Yeah? I'm not sure I understand. I apologize.
WWV, common clock,
Oh.
radio signal.
Yeah, Boulder. But yeah, exactly. Yep, NIST has the atomic clock, so very close by. So you might have the ability to do that here because you guys have all the GPS equipment. I don't. You have another rubidium clock slave to GPS at 10 megahertz.
No, we check into this.
So the SimX does have a GPS input, and you can slave it to GPS. At that point in time, you would want to put in a perfect 10 megahertz. Right now, your clock's 0.002, which means it won't get you much. Not really worth it. It's another cable. You have to wait a few more minutes for the one PPS light to come on. So at this point, because you have a new clock, just leave it at what it has in there and run with that.
Goes back to the
No, it is in theory, but it's not as precise as we're talking about. The one, the CG5 has one in which you can acquire a position as well as set the clock. The clock is set to GPS time, but probably not to the precision we're talking about. It's set very well.
Yeah, but it's probably the same connection. The TNC screw in the back of the connector in the back of the SimX. Screw that in, wait a few minutes, your one PPS light will pop up.
But you're not going to usually have this thing sitting outside.
But if you had a long cable or something like that, or you had a GPS antenna on the roof, plug that in there. Yeah, so for now, for the most part, you won't have to worry about your clock. The rubidium clocks are sensitive to helium. So if you have like a superconducting gravity meter, definitely when you're filling it, or if it's known to be a leaky superconducting gravity meter, be conscious of where your rubidium clock is. It does changes the frequency quite a bit. So to the point where they can't lock at all. And then in order to recover from that, you either have to purchase a new clock, or you just have to wait a really long time.
Yeah, for time.
Yeah. So the helium can get inside the cell and cause issues and change the frequency. Yeah, so you won't have to do much on that page. Older acquisition, let's go to this one instead. Pretty small, sorry. My eyes are getting bad, standing in the back. So we kind of went over this page a little bit earlier. The acquisition tab basically sets up the project. You can tell it, in my project, I want to take 24 sets. In each set, I'm going to do 100 drops. And I want to space out my sets by 60 minutes each. The drop interval and pulse delay tells you how quickly you take each measurement. Right now, from drop to drop, there's 10 seconds, and the pulse delay is how long it sits at the bottom before it lifts up again. And that helps out with, we were talking about that the other day.
What was the lower limit that you said you might see a bounce?
You could safely go to 5 seconds and 5 and 3. I think we've taken it down as much as like 2 and 1, and we see pretty good.
Those Big Tens are very good, very safe.
Yeah. So I 5 and 3 is perfectly safe, and 10-second drop interval is
I'm
fine.
taking several sets of good movement.
So the set interval, you always want to have about an hour, half an hour.
It depends upon what you're doing, right? If you want to try and get into a site, occupy it, and get out within 6 hours or like 1 day, then you probably want to step that up a little bit. We were doing 100 drops over lunch just now, and the quickest you could do was 17 minutes. So we did six times 17, so just under an hour.
We'll have to see how the
Or just over an
logistics work in the field. But if we can get something started and say go with 18, set it for 24, and if we get 18 hours, it's probably a pretty good set.
Yeah.
Pretty good project.
Yeah,
You can
I would.
stop it.
I would envision like an overnight run, so you get in,
Yeah.
early in the morning, set up the system, get running shortly after lunch, let it run all evening, come back the next morning, start turning. If that's the case, then it doesn't really make sense to take more than whatever the numbers. We did the math this morning over on the dry erase board there. Depending upon what your drop scatter is, how many total drops you need, space that out over over whatever time frame you think you have, and that kind of, and then evenly space it out.
However long it says we need to get to 2 million.
1 or 2 milligals. This is the location if we had a new project up where you would be able to set a delayed start. I highly recommend not using that, just because it opens up for errors. There's a couple times like we hit start yesterday and we forgot one cable. If we walked away and it started at 6:30 in the evening, we would have come back in and we wouldn't have had not a single drop. So definitely make sure that it's lifting, dropping, taking data before you walk away. You're pretty safe if you hit go and you take 10 drops and then hit stop, and then you could set up this delay, but at that point you might as well just be taking gravity. So the red-blue sequencing here is if you're running an ML1. You guys didn't get that option, so it kind of doesn't pertain. But basically, the way that ML1 works is there's 2 different modes that can fluctuate quite a bit, but the center frequency is very stable. So you have to measure on one mode, then you have to measure on the other mode, take the average. But so that gets set up in here. Yeah, we kind of talked about the acquisition page, control page. It's funny, this has changed a little bit. So we will just go ahead and look at the live one. So far what we've kind of messed with is the title correction. You have to set that up every time you do a new occupation, or new site. You'll see here if you change the site name, it will make you it'll make you recalculate the title parameter. It won't do it if you just change the latitude and longitude. So you got to make sure that you're changing the site name and rerunning title.
So, but if you do change the latitude, you need to run the ocean mode.
Right. But it just won't warn you. It only looks at the program. So if I do this now, because I haven't run the PTF on my computer. So if I try to reprocess this, it actually warns me, warning delta factor not found. I don't have your title program for the PTF site on my computer. So you need to go in. You'll see like all these files now have a PTF extension. I guess not the top one. Run ocean load. It does pull in. You can see it does pull in lat long. But I'm pretty sure it's not smart enough to know, okay, you changed latitude, but you didn't change the site name. So now if I hit OK, the bars go. At this point, I would be able to reprocess the data. Here you can also set up all the other corrections, barometer, polar motion, transfer height, and change like the barometer factor. This is standard. I suggest just leaving all these corrections on or off. If you want to, you'll have to measure your diffraction, self-attraction. I think we did a big study with that a few years ago, but I think we found it was pretty minimal, and that's just the attraction of the meter itself. Right, so there's a lot of mass. There's the ion pump. There's the interferometer. That all creates different gravity. If it's way up top, it's further from the ion pump, so it doesn't get attracted as much. As you come down, it gets more. So there's actually a correction for self-attraction, attraction of the test mass to the meter itself. Auto peak detect, we talked about a little bit. That tells the computer, okay, read in your 1Fs. Tell me if I'm on EF or G. If you don't have that checked, you can tell it, no, I know for sure I'm on E. No matter what the 1F value says, I know I'm on E. Just make the calculation based off of that frequency of the laser.
If you have auto peak checked, does it matter which one of those you have selected from that drop down?
No.
Okay.
That's a good point. So if I'm here, I can do that, and if it's on E peak, it knows it's on. It's only if this drop down is only if you have that unchecked. So now it says, no, I'm running on G peak. Always monitor your 1Fs. By that I mean have that cable in the front plugged in from the laser to the 1F, and always have that checked. That's the best way to run it. You can change your reject sigma. So this is how many sigma from your average is a drop. If this is bumped up to 4 for some reason. Normally we run at 3. You can even get really fancy and change all of these parameters. These are standard uncertainties that get calculated into the systematic uncertainty. These numbers came from that paper from Tim Niebauer and et al. About uncertainties. Don't need to mess with those. Drop fit. Let me open up a window real quick. Oh, this already has it. Just got to run it. So right now I'm reprocessing data. You can see, I think I'm trying to do a whole bunch, so it's actually going a little bit slow. I've got a bunch of other programs open. PowerPoint in the background running VMware, throwing it up to the screen. So it's actually running kind of slow, but so you can see here, in this case, there was a rejected point that was 3 sigma out. The drop fit sensitivity, that's good enough. At any point in the reprocessing, you can stop it, and it'll just hang out right there. You can pause it up there, and then you replay it. If you stop it and restart it, it starts all over, back over from the beginning.
How come the rejected point has the value of the...
Because it's a different set.
I know you
Oh,
would
that's per set. Okay.
Yeah, so that was the That was a set that there was actually one that was rejected. And then in that set, there were none rejected because it was nice and quiet. So I stopped it after reprocessing the second one. What I wanted to talk about was the fit sensitivities. We'll start at the top. Fit sensitivity shows how sensitive. So we fit the gravity in a window, right? We start taking gravity at the beginning, stop taking gravity at the end, and this shows you how sensitive the gravity number is to that window size. It's a lot to take in. So, in our parabola, right, the test mass starts falling, and we saw that parabola earlier. We chop off a bunch of data in the beginning, we chop off a bunch of data at the end, because as it's separating from the cart in the beginning, gravity could be affected. As it's catching it at the end, gravity could be affected. How much data we chop off at the end, this shows how sensitive the measurement is, how much data we chop off at the beginning.
Is this, the green line on, as you were running it, seemed to sometimes go above, sometimes below. This is that screen, right? So that if you capture a different frame, it might be in a different position.
Correct. Yeah. Yeah, so the blue is the average, the green is just this last drop that got displayed. So if we start measuring, we're probably starting the measurement right around 15 milliseconds. You can see this is in 15. If you go a few more milliseconds ahead, you can actually start as far up as 40 before you even really see it moving at all. And then even out at 60 milliseconds, start taking data out at 60 milliseconds. Now you're talking about maybe 1 micron.
When do you typically start?
Here we're probably starting at 15 milliseconds. That can be set in the setup window under acquisition. Oh, sorry, control. Oh, we're starting at 10. Actually,
How many
10
milliseconds
milliseconds.
does the drop last?
So we're starting here at 10 milliseconds, and we're stopping the data at 50 milliseconds, 250 milliseconds.
So that's a whole drop.
This is actually just the top part of the drop, so from 10 milliseconds to 60 milliseconds.
And then I misunderstood you. I thought it said a full drop was 50.
Sorry, 250.
250, my
Yeah.
mistake. All right.
Yep. So this is only the top,
Gotcha.
1/5. So you can see very insensitive at the top. That's what you want to see. And then at the bottom, for some reason it dropped out the average. And now we're stopping our data here. If you were to stop the data back at 235, maybe you'd be, well, actually the average is up at like 2. And then if you took it out to 260. And one thing you can really makes it obvious if we take this out to 270 and rerun it. So here you can see these data points is when it starts getting into the catch. So now you're down, way down to 10 microgals. And beyond, right? So this is the catch portion. So 150,000 microgals if you're out close to 265. And the problem there is test mass is starting to hit the cart that far out, and it's going to stop and catch it. So you can play with that. Again, I suggest that you just leave this at 10 and 250 like it was set up at the factory. These 4 blocks here just change what is plotted. So I changed this number to roughly 270, and then it plotted out that far. So it's not what actually gets calculated into the gravity calculation. That that make sense? So these two sections are only graphical. This one is what changes the gravity measure. Don't change these. You can change these all you want for display, yeah. And it'll help with diagnostics. If you're having some issues or something like that, we might ask you to open up that window so we can see, like, oh yeah, look, right, you know, at maybe at 255 you're starting to hit or something like that. So if you have problems, you talk with us, we might ask you to do that kind of stuff. This is the fit windows, top and bottom fit sensitivity windows. Again, it tells you how sensitive you are to seismometer. You don't have one, but there's an option that in the future to have another seismometer along the side, so you just have like a vertical seismometer measuring, and at the time of the drop, you can correct for whatever the ground is doing. That's still kind of in the planning phase, but it's an option there. And then
One mile like that. It's a genie. Looks like a seismometer. That run. Just doesn't have
This is like the
yeah, Juan Lorenzo, his G meter is hooked up to for recording device.
line technology thing, or is that too old? That's what it's doing?
And then lastly, the comments page, you can put in the operator, company, and then any notes for the location. We're going to get very familiar with all the controls, so unless anybody had a quick question about this stuff, I think we'll push along with that. One thing I will point out, there is a time offset option up here. So let's say you start your meter, start running, you leave, you come back, and you see a nice tide signal in it. And you realize the computer clock, for some reason, was 5 minutes off. You can go into the time offset, and you can go, okay, the computer thought, or the run thought it was at this, it started at this time. It was actually started 5 minutes later. You can put in that time offset, rerun the system, rerun the file, and get rid of that tide signal.
You can see that signal in 5 minutes.
Yeah, we can. Well, that's a pretty big data file. We can play with that a little bit later. But yeah, definitely 5 minute difference on the clock. You can see it changes the amplitude of the signal, obviously, but I think a couple microgals in a couple of minutes, something like that. So 5 minutes offset might be tens of microgals, maybe 5 to 10 microgals. So not all is lost. If you do find something, the key is just make notes and know how much time offset. Looking for, there is the ability to splice together data. If you have, let's see, we went through all this. This is talking about if you started from a previous file, most of that stuff is already saved in the data. And then you can actually even save a pre-existing file as a template to start for a previously occupied site. This is the acquisition stuff that we talked about. If you're having errors, it's kind of common problems. We've kind of gone over quite a few of those. There are a lot of different windows available to look at. Under View, you can see all of these are different graphical windows that can be displayed either in real time or during post-processing. Right now, we only have the set gravity. You can see the check boxes here: drop gravity, drop residuals, and then the fit windows. Those are kind of the 6 I typically leave up, with kind of the fit sensitivities being optional. I think over there we don't have those selected. Anything that you add, like if I were to add drop histogram, you can see it's blank. You have to reprocess the data with the window open in order to display it. So now if I were to do, basically what this one is doing is it's showing the drop histogram of that set. Stop it there so you can see that we've got 100 drops. Oh, I nailed it. Nice. And it's a pretty even bell curve distribution, which is what you like to see.
Pardon? Yes. 1 signal level, 6 cables.
Yeah, so in the setup you can set your sigma, sigma limit. You can reject either 1, 2, 3, 4, because you wouldn't want to do 1 or maybe not even 2, but we kind of standard reject 3. At that point, if a drop is rejected, it's not used in the calculation of the average gravity value for that set. That's something you can also do in post-processing. Even a rejected drop, all the data for that drop is saved in the
So you
file.
can bring it back.
Yep.
If you have the signal.
Yep. I don't think I'll go through each one of these. The set histogram is similar to this, but for each set. Set sensors, those are all the A to D channels, like the laser and the, I keep saying A to D just from nostalgia, but they're actually all digital channels now that go through the SIMEC. Those are all recorded in the computer and in the file. Even if you don't have the window open, those are still recorded. Set corrections are all the corrections for each set. And then you've got kind of all the same stuff for the dropper. You can even display the drop parabola. Maybe we'll run a few there. So there you can see the position, the distance over time. I'm going to change the scale here a little bit. It's not dropping all the way. So it drops almost 200 millimeters in 200 milliseconds.
What's cool about that is one of the original uses of this that NGA had, was determining absolute gravity for targeting
Okay.
and let's check for heater.
Yep.
In addition to the mission.
Yeah, so those are all those available views that I was showing you. So by default, I think we kind of talked about this earlier. The project file contains the snapshot of the current state of the project, meaning a very general overview. They'll give you a gravity value, kind of your parameters that you had in the file to begin with. And then the set file does the same thing for each one of the sets. It contains a little more detail. I'll switch back over to the program here in a second, and I'll show you those. Those are just text files. Only saves data at the end of each set. So if you stop it midway through, you'll lose the data in that set. But if you've already collected 25 sets, you won't lose that as well. If you reprocess, you only overwrite any changes you make to the setup file. You don't actually lose any of the data or anything like that. So here, this is why we make a new folder every time we make a new project. These are all the files that it creates every time you do a project. Each one of these GSF files is each set. That keeps all the set data. And then the .project, that project overview that I was talking about, .set, is the set file. Oh yeah. If you were going to transfer or archive files, make sure to include all of these files. Definitely the GSF and the .fg5. Where is that guy? Oh, doesn't have the extension. But it's safest just to copy over all whatever's in that folder. Excuse me. Yeah, you can take out sets. This is all talking about. There are tools, gmerge, to if you had, so you had two project files that you know had a gap of 24 hours in the middle. You want to put them into one file. You can do that. Not sure what that is used for, but if we have the option, somebody at one point in time asked us. So that way, you can just same occupation. You can see two different files in one, two different measurements in one file. All right. I know I said it'd be quick, but that wasn't the quickest. I apologize. Any questions about the interface with G and what it can do?
What which of those files would you click on? Say if you want to just open up the 4 tile view in G, open up the project.
Good question. All right. So if, let's say,
Is it the FG5 file or the project?
yeah, by file. Yep. So if let's say I just opened up G and I want to reprocess that file that we just had.
Now, do you have, when you would click on that file, that FG5 file, when you click on it from just Windows Explorer, and G will come up automatically, or does it have to be done with G?
Good question. It actually has to be done from within G. Yep. So you have to open up G first, go to the location where you stored that file, and then you'll have this FG5 file here. Click on it, and it'll pop up.
So all the set files, GSFs or whatever, they all point to this or vice versa?
Vice versa. This points to the GSF files. Yep. And then because I had all those windows open before, it popped up all the windows. So if let's say you only want the state window, you want the sets, you don't want the fit sensitivities, and you want fit residuals and drops. So we'll close everything else. Tile, you can either do window tile, or you can just hit the T. Didn't work. And it'll pop up the 4 windows that you have open, tiled. Something I kind of breezed over. Everybody wants to know what the gravity value is, right? So in your state window, this is the state window, under project, your gravity is listed right there. And it's the same as your cumulative mean gravity down here under sets.
That's in that set.
Because I only ran one set, yes, you're right. But if I were to let several sets run, you'll see like this changes with each drop. This
Like gravity
changes.
is for however much you've processed on it before.
Right. Yep. So now the drop, let me slow this down just a little bit so we can, so if you go into rate, is it options? Process rate. It'll pop up with a display window. You can change this to like 200. And what that did now is, now instead of 1 millisecond for every drop, it's doing one drop, reprocessing one drop in 200 milliseconds. You see it slowed way down, and you can kind of visually watch the data go through. So with each drop, you'll see that this number changes. With each drop in the set, the average will change a little bit of the set. And then after each set is complete, this number will change for the average of the project. Once you've reprocessed the full data, this is the number you're really interested in, and it will be also the average of all the sets. So
Now, on this, as the sets accumulate, where is the window for your standard deviation? Your sigma?
right now we have it set to 3 sigma.
No, but I mean, for this, this value, what is the 1 sigma value in micrometers?
Okay, for this set, the drops right here, you have a
For more than one set.
for all the sets. So you have the standard deviation of the sets is plus or minus 2.19 microgauss.
Gotcha.
And you can also see in set total uncertainty right there. It's kind of hard. Excuse me. It's kind of hard with
So
with
when
it
they're
moving,
out in the
but
field, they know what about what they want for a standard deviation for the goodness and fit of their data.
Right.
So as they accumulate sets, they can look at this, and when they reach the target standard deviation, they don't need to occupy any longer.
that will actually be in your uncertainty here under project. So once you kind of get to 2 microgauss there, and you'll notice that it won't, like, every time you get a new at this point, every time you get a new set processed or run, that number won't change much.
And that's what that formula is right there.
Basically. This number takes the number on the board and adds it in quadrature with our systematic uncertainty. Quadrature, the square root of the sum of the squares. There's the other equation on that one. I know you guys got a lot of information yesterday. I totally understand that. But you'll get that slide, and I'll write up on the board here in a second. But it's basically the systematic uncertainty squared plus the statistical uncertainty squared. Take the square root of that, and it gives you the total uncertainty.
Because the deviation starts to get lower and lower, and then starts getting larger again. When you buy a school, go outside and screen recesses over. And kids aren't running around.
Maybe you
You
see the one
500 kids.
did. Going to
So yeah, I can go process, rate, go back to 1. Let's just finish this up. Sometimes the graphics lock up and it just does it on its own. Now you can see that we're flying through. We're already on set 16, and we only got one more, so now we're done. So.
2.17.
This is the window. This is the one that you can't really do anything about. These are the uncertainties, sources of error. That's 2.15. So if you add that, like I was saying, the squared of that plus the squared of your basically this equation on the board will give you that 2.17.
those are the values you said.
These are kind of standard industry accepted numbers. If you ask just about anybody, Dan Winchester or Wheeler or anybody, all these numbers should be roughly the same. Some people like to change them, but but this is our best suggestion. But this is definitely part of the science. So. Okay, I'm done talking, but I'll more than happy to answer questions. Tear down a gravity meter and put it back up. Thank you.